cationic addition and anionic addition. That's where we're going to start. That's like some of the most important things that you have to know in chapter 27. So chapter 27, like I was telling everybody, synthetic polymers, everything that we've dealt with up until today in organic chemistry pretty much has been mimicking some kind of natural compound or something when we look at drugs. But now we're just going to talk about synthetic polymers. So these are polymers that are made in the lab. Can you have a biological polymer? Yes, and we'll talk about that in just a second. But just to keep this, just to put this out there, some concepts you're going to see in this chapter are going to be alkanes. And if you're like, well, I already know those, we cover those in chapter 4. Absolutely. Then we're going to talk about cationic polymerization and polystyrene, and it's borrowing some chemistry from chapter 8. Trust me, you'll figure it out once I show it to you. And then the last part, it says radical polymerization. So if you remember the old fishhook arrows that we looked at, like let's say you had two radicals, you have two different radicals, two different radicals like this, and then you did a termination mechanism, right? You guys remember initiation, propagation, and termination, and of course these would come together to make some kind of non-radical. So we're going to see some fishhook arrows in this chapter. And why can we not leave polymers out? I mean, come on, give me a break. I mean, this says the U.S. alone, just one country produces 50 trillion pounds of synthetic polymers every year. And like I was just saying to my students before we started recording this video, I said they're everywhere. My Apple Pencil is made out of polymers, my iPhone, my calculator, even the covering on my desk. My brother-in-law bought me a desk, and the cover on it is a polymer. What else? There's polymers in the carpets and the fiber in the room that I'm in right now. My binder, I have a cover on the binder that's made out of polymers, and I could keep going and going and going. And so modern day society, we're pretty much completely dependent on polymers in every part of our life. And so we would be remiss to leave the class without talking about polymers. Now, if you've been looking at all the different discussions throughout the textbook, you probably noticed that polymers have come up in a few of them. So you see they came up in many different chapters. I didn't expect you to read those all along the way, but we did talk about proteins in quite a bit of detail in chapter 25. And we're going to talk about cations in this chapter. So, this is going to be something that you know pretty well. And then we're also going to talk about radicals. Like I just said, you're going to see the fishhook arrows come up in this chapter. And if you remember in chapter 16, this semester, we talked about dienes and esters and amides and polysaccharides like cellulose and amylose and amylopectin and all that kind of good stuff. So how do you make a synthetic polymer? Well, synthetic polymers are comprised of repeating units made by joining monomers together. So the two key words here are polymers are made from monomers. So we take monomers, we put them together, and we repeat them over and over and over, and that's how we get a polymer. And if you just take a look at these monomers here, you see they're all identical, and they're all some kind of derivative of ethylene, right? You guys know that if you have CH2, this is ethylene. You could call it ethene, but the common name is ethylene. So these are some kind of ethylene derivative. And then we take those polymers and those monomers, and we put them together to make a polymer. And I'm sure you can connect the dots very quickly that all you do is write the monomer without the double bond, right? You just keep repeating it, the monomer without the double bond. And then to make the polymer, you just connect it, right? So you just connect, and there you go. You, my friend, just drew a polymer. That's all there is to it. So we just eliminate the pi bond is all we're doing. And instead of saying, well, this is going to repeat, thousands and thousands and millions of times, what we do is we find the shortest repeating unit, which you see in these dashed circles here, and then you put it inside square brackets and put a subscript n to say this is repeating n number of times, okay? So that's the shorthand structure that we use, and we're going to get some practice on that today. And like it says here, connecting only the atoms in the bracket, okay? If you connect the atoms that are in here over and over, it should give you the actual polymer's structure. So when it comes to naming polymers, we've already finished the first section. When it comes to naming polymers, there is a systematic way of naming polymers, although it's not often used. And so we like to use the common way of naming polymers, and I don't like to use the word simple in an organic chemistry class. I don't think it belongs here, but I'd say it's relatively straightforward. All you have to do is look at the name of the monomer. Okay, if you know the name of the monomer, propylene, When you make the polymer, you would call it polypropylene. So you just put poly before it. If you have styrene as your monomer, well, you guessed it, the polymer is going to be polystyrene, right? So, and if you're thinking polystyrene, isn't that styrofoam? Well, the first styrofoam was made completely out of polystyrene, but we'll talk about that a little bit more later on. And then, of course, we have all kinds of trade names that are used for polymers. I'm sure that everybody who's hearing the sound of my voice has heard of Teflon before, right? It's used in nonstick cook pans. And of course, Kevlar, which is found in bulletproof vests and helmets. And, you know, being a Canadian, it's also found in canoes. All right. Anyhow, so it says here nomenclature of synthetic polymers. So let's take a look at some monomers, right? Everybody here should know the structure of ethylene by now. And so if we were to make a polymer of ethylene, what do we do? Okay, so let me show you kind of the shorthand way of doing this. If you're ever faced with a question that says, what is the polymer of this compound? All you have to do is remember, these carbons in the monomer are sp2 hybridized, but in the polymer, they're going to be sp3. So we draw our bonds at 90-degree angles like this for a polymer, okay? So I've got everything that's in this structure drawn in blue here on the left, except I don't have the pi bond. So you break the pi bond when you make the polymer. You put two bonds, one off of each end, put square brackets around it, and then just write N like that. And there you go. That is your polymer. And you see that right here. And so we would call that polyethylene. Okay, so polyethylene comes from ethylene. So again, this is ethylene. The next monomer is propylene. Propylene. And you could also call it propene. That's fine, but propylene is the common name. And so if we were to make the polymer of propylene, we get polypropylene. And polyethylene, you might have heard of it before because it's found in very cheap plastics like trash bags and disposable bottles and things like that. Whereas polypropylene, it's found in carbon fibers. I would also put fibers. I would put ropes in here. So it's also found in ropes that just last a long time and are very strong. Also, I'm not sure, I'm sure propylene or polypropylene has many uses in appliances. And then it says here car tires too. If you've ever studied how car tires are made, it's actually a pretty complex process. And polypropylene is found in those. Then we move on to isobutylene. So this compound down here, this is called isobutylene. And I'm sure you've picked that up along the way in the course. You've seen it many times. We saw it, in fact, in the last chapter when we talked about the deprotection of the Bach group, and we said it liberated isobutylene, which is a gas. But anyhow, if you have isobutylene, the polymer you would make from that would be polyisobutylene, and that's found in like sealants and caulking. And then it says here also inner tubes and basketballs. I know that butyl rubber is found in basketballs, but I'm sure that the you know, building a basketball isn't that simple. So I don't know everything there is to know about building basketballs or inner tubes. But anyhow, there you go. The next one, styrene, which you saw came up a little, just a couple of seconds ago. And you probably recognize styrene because I asked you to memorize its structure way back in chapter 16 and 17. We said, okay, if you have an aromatic ring, okay, and then you have an ethylene group coming off of it like this, this is styrene. Well, that's what this is here. It's just written in a different way, right? They just wrote it as pH, and then they put the ethylene off of it like that. So styrene, from that, the polymer we would get would be polystyrene. And yes, the initial styrofoam, the very first styrofoam that ever came out decades ago, was made completely from styrene. It was just polystyrene. However, they found that it degraded rather quickly. And so now they add other compounds to it to make the modern styrofoam, but it is found in foam insulation. So you definitely find it there if you've ever put foam insulation in a basement or in a wall or something like that. Televisions and radios, I'm sure it's got some use in those. So let's see here. So you guys know styrene. You don't need me to help you with that one. The next one is vinyl chloride. So this one is two words. So vinyl chloride, okay? And if you have a polymer that has two words in its name, when you're giving the name of the polymer, so did I say that right? When you have a monomer that has two words in its name, like vinyl chloride is two separate words, when you're naming the polymer, you put poly, so you see here you put poly, and then you put an open bracket, vinyl chloride, and then a closed bracket. So we always do that when we have two words in our monomer's name. All right, and then it says here polyvinyl chloride. Of course, you guys know that one, right? PVC, right? You find that in water pipes. You can go to Home Depot and buy all kinds of polyvinyl chloride pipes. And the next one is always a fan favorite. So it's made from methyl alpha cyanoacrylate. So this compound here, this is methyl alpha cyanoacrylate. How's that for a name for you? So methyl alpha cyanoacrylate. And what's cool about this compound is it polymerizes really easily, right? So when you polymerize that, you get polymethyl alpha cyanoacrylate, and you see that that's found in superglue. Now, I hope this has never happened to you, but I'll just ask: is thumbs up? Has anybody ever gotten superglue on their fingers before? Has this happened to anybody? I can admit it's happened to me, okay, more than once. You know, I've even used it one time when I was on a hunting trip, you know, and I cut my finger open, and one of my friends happened to have super glue, so I put it on the cut to fix it up. But anyhow, we're going to talk about polymerization and the mechanism of it in a few seconds. But to initiate the polymerization here for super glue, you have a strongly electron withdrawing group here on this carbon, and you have another one here. And so just a little bit of water, it's not a very good water molecule, is it? Just a very little bit of water in the sweat on your fingers, okay? All it has to do is see this carbon and it attacks it, okay? And that initiates the polymerization reaction. And we're gonna look at that in a little bit, but there you go. Now, if you're wondering, I've had students ask me about super glue to put it on a wound before. And if somebody says I've gotten super glue on my fingers way too many times, I can relate. So sometimes people ask, well, when don't they put that on cuts at the hospital? It's usually not super glue that they would put on there. It's something called Dermabond, which is very closely related. Instead of a methyl group here, you have a 2-octyl group, and that's where Dermabond comes from. Anyhow, there you go. So what else? So this one's a repeat from the last slide, and this one's another one of my favorites. Does anybody like cooking with Teflon cookware? So this is tetrafluoroethylene. So tetrafluoroethylene. It's like you got Tefal. Well, I've got Teflon. It's got to be Tefal. Anybody know what I'm talking about? George Costanza's father. Anyhow, so polytetrafluoroethylene, which you guys know as Teflon. Has anybody ever heard of Teflon? Please tell me you guys have heard of Teflon, that somebody has. Yeah, okay, good. Okay. So Teflon, you guys know quite a bit about intermolecular forces at this point in your chemistry career. Now you think about fluorine. Fluorine is a very small atom and it's non-polarizable, right? Remember that as you go across a period, the elements get smaller and smaller. And since fluorine is so small and non-polarizable, it doesn't create any intermolecular forces with anything around it. And that's why if you coat your frying pan in tetrafluoroethylene or Teflon, it doesn't stick to anything, you know. Obviously, it can wear down over time, but generally speaking, it's going to be a lot less sticky than something like cast iron, okay? So there we go. So the next one just says, draw and name the polymer that results when each of the following compounds or monomers undergoes polymerization. Now, with these ones here, I don't expect you to know the name of every single monomer. I would give you the name of the monomer. For example, the first one, this is vinyl acetate. So vinyl acetate, and don't panic. I wouldn't ask you to just pull that out of thin air. And then the one down here, this is, I mean, you guys know it is 1-butene, but the common name is alpha-butylene. So alpha-butylene. Okay, so I would give you those. And so if we wanted to give the name of the polymer, for the first one, we would call it polyvinyl acetate. But let's try drawing the polymer. So we're going to start with the first carbon, which has 2 hydrogens attached to it. Okay, and that's this one here. Then we're going to draw a single bond to the next carbon, which has the acetyl group attached to it, or the acetate group attached to it. Now what we're going to do is we're going to repeat that. Okay, so we're going to do it again. And you can do it as many times as you want. Okay, I'm just going to do it twice, just in the interest of time. Okay. And even if you just did it once, that's totally fine. So now we're going to put a square bracket around both ends, and we're going to put an N like that, okay? But again, if you had stopped, I'll just erase this and show you. If you stopped here and said, I'll just do this, okay, and then just put an N like that, it's totally fine. And say poly, and since it's 2 words, you use a bracket, polyvinyl acetate. like that, close brackets, done. Okay. Next one is alpha butylene. So let's try drawing the polymer. So we're going to have our CH2 like this. Then we've got our carbon with our ethyl group. Come on, CH2, CH3, like that. Okay. All right. There we go. So this would be the this would be the polymer, the way we would draw. Yeah. All right. So we have poly alpha butylene, like that. So poly. Give me a thumbs up if you think you could do that. I shouldn't even ask. I know you're all more than capable of doing it, probably faster than me. Okay. So there you go. Let's just take a second here